the next speaker is Sunita. I'm going to try Chepuri.
That's right.
Who is going to talk about K-positivity of the dual canonical basis. And you have to wait 3 seconds to start. Ready? Go.
Okay. Well, thank you to the organizers for having me. And this is joint work with Melissa Sherman Bennett. So first I'll give an outline. Okay, I have 2 terms in my title that are maybe not familiar. So first I'm going to talk about K-positivity, and then I will talk about the dual canonical basis. And the dual canonical basis is like not a friendly object to study. So we're actually going to be using this other object called an immanent to study the dual canonical basis. So I'll introduce those as well. And then I will share our main theorem, and if time, a little bit of a sketch of the proof, and then we'll talk very briefly about some future work. Okay, so we're starting with K-positivity. So we say a matrix is totally positive if all of the square submatrices of that matrix have positive determinant. So as an example, here's a matrix A. So all the 1-by-1 submatrices, those determinants are just going to give you the entries of the matrix. So we can look at this right away and see all of those are positive. There are 9, I don't know if it's clear, there's a space here. There are 9 2-by-2 submatrices, and you could check all of them if you feel so inclined. They all have positive determinant. The determinant of the whole matrix, which is the only 3-by-3 submatrix, is 2. So everything is positive, so A is totally positive. Okay, so why would we be interested in such an object? So these matrices first came up in work of Schoenberg in 1930. So he was looking for matrices that have this variation diminishing property, which is essentially means that when you multiply them by a vector, it doesn't increase the number of sign changes in the vector. And there are reasons in physics for looking at this. And so the matrices he found with this property were these totally positive matrices. And then completely separately, at around the same time, they also came up when Gottmacher and Krein were looking at various matrices that had good spectral properties. And they found out that these totally positive matrices, if you have an n by n totally positive matrix, it has n distinct real eigenvalues. So these works were completely independent, but they came up with the same group of matrices. And so since then, people have found applications for these matrices in all sorts of areas in math. And for me, as a combinatorialist, there are a couple of reasons that I'm interested in totally positive matrices. First of all, they have a really nice relationship with networks. And they also were one of the motivations for the development of cluster algebras. And they also have a really nice topology. So hopefully this is enough things that you think, okay, maybe there's something going on with these matrices and they're worth looking into. Okay, so, but we're not going to talk about totally positive matrices. We're going to talk about K-positive matrices. So we say a matrix is K-positive if all of its square submatrices of size less than or equal to K have positive determinants. So this is a weakening of the total positivity condition. So here's an example of a matrix M. So my 1-by-1 determinants, I can, again, just look and see they're all positive. The 2-by-2s are also all positive. So M is 1 positive because these ones are positive, and it's 2 positive because all of these are positive. But if I look at the matrix that lives in rows 1, 2, 3 and columns 1, 2, 3, the determinant of that guy is negative. So that means M is not 3 positive, and also it's not 4 positive or totally positive. So these matrices have many similar but slightly weaker properties than totally positive matrices. And so one of the things that I've been studying is just in general, how much of what is true for totally positive matrices is still true in this case. So I've done some work looking at the topology of these matrices, looking at the cluster algebra structure of these matrices. And today we're going to talk about how they relate to the dual canonical basis. Okay, so what is the dual canonical basis? I'm not really going to tell you what the dual canonical basis is. So we're going to let G be a reductive group. And I'm just going to say the dual canonical basis of the coordinate ring of G is a family of functionals on G. And the reason that this relates to our positivity story that we've been looking at is that Lusztig defined for this reductive group G, the totally positive part of G, and showed that all elements of the dual canonical basis are positive on this totally positive part of G. And further,
excuse me, can you say briefly what a reductive group is?
I'm gonna ignore that. It's just some Lie algebra thing. Everything we're gonna do is in SLN, so you can ignore that if you don't know what it means. So yeah, okay, so further, Fomin and Zelevinsky showed that this totally positive part of G is exactly the subset where certain dual canonical basis elements called generalized minors are positive. So we could take this to be our definition of the totally positive part of G. So the very broad question is, what if only a subset of these generalized minors are positive? What does this tell us about the positivity of the rest of the dual canonical basis elements, right? So if all of our generalized minors are positive, then we know we're in this totally positive part of G, and then we know that all elements of the dual canonical basis are positive. But what if we only know that some of the generalized minors are positive? So as I said, everything that we're going to do, this slide is sort of a really broad overview, a question that we would like to eventually someday get to. But right now, we can only answer this question like in a very, very specific setting, which is we're going to have G be SLN. Actually, most of what we do applies for GLN, but the statements of the theorems look less nice. So we're going to stick to SLN. Our generalized minors are just minors, which I didn't introduce this terminology, but this is those determinants of the submatrices. And then we're going to require that the minors of size less than or equal to K be positive. So our setting is we're looking at the K positive part of SLN. Okay. So on the previous slide, I didn't at all give you a definition of the dual canonical basis. So I'm instead going to define these things called immanents. So we're going to let X be just the matrix of indeterminates, and we're going to define all of our immanents as functions on X, and we could stick any matrix in for X, and we would get the function evaluated on that matrix by just substituting in our entries of M for these indeterminates, Xij. Okay, so if we have a function from the symmetric group to the complex numbers, we can define the immanent associated to that function to be the sum over all of the elements of the symmetric group, where we evaluate F on that element and then take the matrix entries given by that element. So one immanent that everyone has seen is if F of W is the sign of W, then this immanent is just the determinant. Another really common immanent is if F of W is always 1, then we get the permanent. And in general, if F is an irreducible character of Sn, these are irreducible character immanents, and these are the ones that are sort of most commonly studied, at least classically. But we are going to talk about these other family of imminents called Kazhdan-Lusztig imminents. So our F is now this -1 to some power times this guy, which is the Kazhdan-Lusztig polynomial evaluated at 1. You don't need to know what the Kazhdan-Lusztig polynomial is. You just need to know that they are defined. They're just hard to compute. I could put the definition up. It's a recursive definition, but it wouldn't be very enlightening and it would take a while. So we're just gonna kind of ignore what that means and just know that it's something that's hard to compute. Okay, so in order to state state the relationship between imminence and the Kazhdan-Lusztig imminence and the dual canonical basis, we need some notation. So we're going to always let R be an n element multiset of the set 1 through m, where the elements are listed in increasing order, and same thing for C. So then for an m by n matrix, we define MRC to be the matrix that has in row I, column J, it has the element from M that was in row RI and column CJ. So maybe it's easiest to see with an example. So if this was our matrix M and R is 1, 1, 3 and C is 2, 3, 4, we just think about, let's look at M. We're going to repeat row 1 twice. We're not going to have row 2 at all. We're going to have row 3 once. We're not going to have row 4 at all. And then we're going to have columns 2, 3, and 4, but not column 1. So that ends up giving us, that's not a good highlighting. That ends up giving us this guy. So you can see we have 1863 because we have this 1863 in the first row, columns 2, 3, 4, and then it's repeated here. And then in the last row here, we have 2, 1, 2 coming from there. Okay, so Skandera proved that the dual canonical basis of the coordinate ring of SLM consists of the non-zero elements of this set, the imminence on XRC for sort of arbitrary RC and arbitrary permutations B. I guess I flashed that very quickly. Yeah, so this is the theorem that's going to allow us to, instead of studying dual canonical basis elements, we're going to study these imminents, which are in certain cases at least a little easier for us to deal with. Okay, so now we'll get to our main theorem. So to state the theorem, we need to introduce the notion of pattern avoidance. Okay, there's a definition there, but I think it's best seen in an example. So let's have W be this permutation 2, 5, 3, 4, 1. We can ask, does W avoid some pattern where, so notice this is in S5, our pattern is going to be S in S something else that's less than or equal to 5. So here, this is in S3. And so what we're looking for is a subsequence of W in one line notation where the sequence has the same order relations as 3, 2, 1. So where the biggest one is first, and then the next biggest one, and then the smallest one. So in this case, we can see we have the sequence 5 and then 3, 5, 3, 1 lives inside here. And 5 is greater than 3, which is greater than 1. So it has the same order relations as 3, 2, 1. And so W is not 3, 2, 1 avoiding. Let's look at a different pattern. So we can also ask, is W 3, 4, 1, 2 avoiding? So to look at this, we want to look at all of the sequences of subsequences of length 4 that are in here. So here are all of them. We could just get rid of the 1, get rid of the 4, get rid of, oh, this should have the 3 gone. Wait, what happened? Oh, this one just shouldn't be here at all. Sorry. This one has the 3 gone, this one has the 5 gone, this one has the 2 gone. So ignoring the one that's currently highlighted, these are all the subsequences of length 4. And we can see that in this one, this one, this one, and this one, the smallest digit appears last, which doesn't match here because here the smallest digit appears second to last. And here the smallest digit appears first, which again doesn't match here. So we can say, yes, W is 3, 4, 1, 2 avoiding. Okay. So we'll say a matrix functional is K positive if it's positive when evaluated on all K positive matrices. And now we can state our theorem. So if V, a permutation, avoids these 2 patterns, 1, 3, 2, 4, and 2, 1, 4, 3, and also meets this sort of funny condition where if we look at in one line notation, every time we have an increasing sequence of size 2, either the difference between the positions is less than or equal to K, or the difference between the numbers in that increasing subsequence is less than or equal to K, then this imminent is either identically 0 or it's K positive, which means that the elements of the dual canonical basis described by all of these guys that are not identically 0, they are all K positive. So I'll just give a quick overview of the main tools that we used. So the first thing we use is this construction of gamma sub P. So if P is a subset of the symmetric group, so for example here, P is this subset, we can describe gamma sub P by first, since all of these are in S4, so our N here is 4. We'll draw a 4x4 grid. And then we're going to put some dots in this grid based on these permutations. So let's just look at the first one. Since we have a 2 in the first place, we're going to put a 2 in the first, in the second, or we're going to put a dot in the second column of the first row here. Now we have a 4 in the next place, so that's going to give us a 4 or a dot in the 4th column of this next row. And then we have a 3, so we'll get a dot in the 3rd column of the row after that, and then the 1. So that's what we get. That's our contribution from this first permutation. From the next permutation, okay, we get a 3 first, so we'll get a dot there. We have a 4 in this second position. There's already a dot here, so we don't do anything. We have a 2 in the next position, in the 3rd position, so we'll get a dot in the 2nd column here. And there's already a dot for this 1. And we get those from the next permutation and this from the final permutation. And so we'll define M restricted to this gamma sub P by just taking everywhere that there's a dot here, we're going to leave the entries of M as they are. Everywhere where there's no dot, we're going to replace the entries of M with zeros. And so we showed that if V avoids those 2 permutations in our theorem, then we actually find that the imminent of XRC is -1 to the length of V times the determinant of XRC restricted to gamma of the interval from W to W naught in the Bruja order. And so then we use Lewis Carroll's identity to do induction. Okay, so the last thing I'll say is just a few brief words about future work. So first of all, we would like to extend this result from the group of 1, 3, 2, 4 and 2, 1, 4, 3 avoiding permutations to a larger class. The reason that we needed to avoid those permutations is because of the relationship between the Kazhdan-Lusztig polynomials and Schubert varieties. And so this allowed us to calculate the Kazhdan-Lusztig polynomials that showed up in our expansions really easily. But in general, those are hard to compute. So that's the I guess, roadblock to extending our result to a larger class. And then secondly, we'd also like to explore the relationship between these imminents and cluster algebras. So in the case where K equals 2, the imminents that show that that we get, we can show that those are all cluster monomials. We don't know if that's true in general, but we would like to explore that more. So I will end there. Here is our first paper where we dealt with the case where we didn't do any of the repeating rows and columns stuff. And then here's the follow-up that includes the results that I showed you today. Thank you.